Welcome to the second day, to the first lecture. Welcome, sir. Now I'll ask Jangir sir to present his presentation on hydrogen electrolyzer principle, technologies and electrical modeling as a first talk of the day 2. Thank you.
So yesterday we talked initially about introduction to the green hydrogen system. Then we talked about fuel cell, like the principal technologies, and then we talked about fuel cell modeling, and we'll also, through the tutorial we practice the modeling in MATLAB as well. So today in the first lecture I'm going to focus on electrolyzer principle, technology, and then finally modeling. So they are like with electrolyzer and fuel cell, you know that it's like a electrical motor and generators, right? So in electrical machine, when it's generator, we use like mechanical energy as input and electrical energy as output, but for the motors is opposite. Electrical input and mechanical output. So here, like for fuel cell, the chemical energy is input and electrical energy is output, but here for electrolyzer is opposite. So it's electrical energy is input and the chemical like hydrogen as output, right? So like when you will be talking about modeling, like in mathematics, you will see like almost quite similar, because it's just like a difference between input and output. So in cases like the voltage equation, you saw that there would be like a internal voltage and the losses minus, but here it would be like a plus. But at the end, and in terms of the name of the technology, also quite similar. So you might see that we are discussing quite similar thing, but it's not similar. So but anyway, I'll go quickly about this modeling technology and principle, because as I mentioned that at the end I'm going to also talk about like not only this lecture but every lecture, what are the like possible future research direction. So I'm going to also talk about some of the future research direction in electrolyzer as well. So again, these are the contents. So we're going to be talking one by one. So again, as I mentioned yesterday, so the electrolyzer use like electricity, and that actually used to break the water. And you know that when we break the water, what we get? Hydrogen and oxygen, right? And similar like fuel cell, it also has got anode and cathode, right? And in between anode and cathode, we have electrolyte. And what are the function of the electrolyte? Just to transfer the ion either from anode to cathode or vice versa. And as we mentioned that electrolyte, which is one of the most costly component in both technology, so it works like a separator, right? Anyway, if you just see that internal chemical reaction, again it's quite simple. So like fuel cell, electrolyzer also has got a number of application. So you can think of like electrolyzer, when it is connected in the electrical power system, you can think this is like a control load. So this is a load, actually you can control whatever the power coming from the electrolyzer to produce the hydrogen, you can operate that is like a control load. And when it is operating like a control load using inverter, converter, that's how you can also provide ancillary service to the to the grid, because it actually response time very fast. So, when you have got response time very fast, that means it's quite flexible, right, and as I say, like the controllable as well. So, for example, let's say if the grid has problem with the over voltage, right. So, by controlling this electrolyzer as a load, you can actually address that over voltage problem, because although this is a load, but as I said, this is a control load, and that is how it can solve many of the grid problems that has been introduced by large scale renewables. So, again it has got application for industry, transport, energy storage. So, in the transport, that many of the vehicle can use green fuel like hydrogen, like car, buses, trucks, and that can be utilized to decarbonize the transportation sector. And as you know, it can be used a potential energy storage as well, like the battery. And in many cases, even I'll show one example that in many cases it can provide actually better ancillary service in some cases. Power to X, you might know that this can be like a power to gas, synthetic fuel, ammonia production, and renewable energy. That's I mentioned that for large scale renewable integration, electrolyzer can also play a significant role as well. The advantages you already know, like zero carbon, flexible operation as I mentioned, and another very important things that it has got very fast dynamic response. And why actually we need fast dynamic response in the next generation power system? Because as you know that we are replacing most of the high large scale synchronous machine which provide inertia service to the grid, right. So, when we do not have like large machine, what will happen? If anything happens, you will find very fast changes, like for example, fast change in the frequency. But when like you have got synchronous machine, as it has got very high inertia, it takes time. When there is a fault, due to that inertia, the changes happens comparatively in a slowly, not like very fast. But once we do not have the synchronous machine, anything happen, you will find very fast changes in the frequency voltage. Now, to address that problem, what we have to do? The control response also has to be very fast, and that is why like the fuel cell, it has got very fast dynamic response, and that actually can be utilized when we do not have like many synchronous machine in the system. But again the challenge we already mentioned, like the fuel cell, this is also comparatively higher cost, some problem in the degradation of membrane and catalyst, which is quite expensive, and frequency drop at very high current density as well. But again this is challenges, but it is not that cannot be addressed. We just need like more research and development work to address those issues. Now again I am not going to take longer time, because I think you have seen similar type of application many times. Again you can see again that's in the left hand side, you have got water and electricity, which is producing hydrogen and oxygen, and here also you can see that you have got anode and cathode. What happened in the previous cases? We have hydrogen and oxygen as input, like in anode and cathode we have got input hydrogen and oxygen, right, and we got electricity as output. But here you can see that electricity is coming as an input, but hydrogen oxygen is like a output, and also previously we got water as a byproduct output, but here water like a input, right. So, that is only the difference. So, what is happening here, like again in the like electrolyte or separator, depending on what type of electrolyzer we are using, that actually giving that electrolyzer name. So, in some cases it could be like PM, then it would be different electrolyzer, but if it is alkaline, then it would be like I mean if you remember that potassium oxide we mentioned for previous cases. So, only the difference would be that electrolyte part. But again what is happening like in the anode side, from water we are getting oxygen, ion, proton and electron, right, and then proton and electron I mean that ion will passes to the like the cathode, because I mean this is for I mean this equation actually for PM, but the figure is showing like alkaline, that is why the direction is opposite. But here proton is coming this way, and then proton and electron I mean at the end is just like producing hydrogen. So, that is quite simple equation. I already mentioned this one, but again I mean for your own benefit, if you like forget later, you can just read this slide, which will give you like how like electrolyzer works and what are the inside electrolyzer components. Now, this is bit of history of different generation of electrolyzer. So, if you see that first generation electrolyzer, that actually that time there was like biggest changes going like all the economy like for industrialization. Before that it was agriculture and other sector was dominating, but that time there was the biggest challenges I mean to go for the industrialization. And what was the technology breakthrough regarding electrolyzer? Previously that diaphragm which used like as the like electrolyte, the separator between anode and cathode, but after that membrane was replaced by that diaphragm was replaced by membrane. And then what was the significance? That industrialization of I mean alkaline water electrolyzer actually started. Then in the second generation what happened? Once we have that technology, the problem was the power density. So, here in the second generation main objective was that how we can improve the power density, and then to do that we got that PM which does utilize polymer solid electrolyze, and it has got higher density. So, and main application was like the life support application like the space program, that time that was the main application. Then once we have got higher density in the electrolyzer, then the next challenge was that how we can reduce the cost. And then we have like different redesign of different like a complex system and doing optimization and so many things I mean to reduce the cost, but still I mean we haven't got that point which is produces hydrogen and cost is lower than the gas, but still I mean after coming of the PM water electrolyzer, I mean the production and utilization have gone up significantly. Then in the fourth generation the main objective was still I mean how we can reduce the size and how we can make it more compact, and still I mean the cost still I mean issue, because we are still continuing how we can reduce the cost further. And here as we managed to get reduce the size, now we have like breakthrough in the technology that megawatt level electrolyzer I mean already available, and you will find many demonstration of large scale application for power to gas as well. Now again incoming fifth generation which will come maybe 2040, 30, 40, 50. Here again the main challenges, as I say, still how we can reduce the cost, how still we can reduce the efficiency, and also its lifetime as well. how we can do that? Maybe we can have a new breakthrough in the novel materials, and also like we might have, instead of megawatt, maybe for coming years our target would be gigawatt level, which like grid connected. So even if you see that name of the electrolyzer is quite similar like fuel cell. So again you have got alkaline water electrolyzer, this is only the difference. And then PEM, that is also quite similar, solid is also quite similar. So I'll just go very quickly about this one, I'll not take time because it's quite similar. So here again you see that both cases, I mean the output is oxygen, and here in both side cathode and anode we have got quite similar type of chemical reaction. So in the cathode you see the from water and using the electricity like the free electron, we are producing hydrogen and oxide ion, and this oxide ion is going to anode via this membrane electrolyte, and then we are in the anode side that ion, and from ion actually we are producing water, oxygen and free electrons. So that's how I mean it produces hydrogen. That's I already mentioned those, and these are the sum of the values. I mean typical value parameter. If, again I mean if you want to do any modeling, so these are the sum of the parameter actually you can utilize for the modeling purpose. But the good thing for most of the electrolyzer, even like PEM, that 99.99 hydrogen purity, but this is again I mean this one also more than 90% hydrogen purity. Yeah, I mean advantage again quite similar, well established, robust technology, lower cost compared to PEM or solid oxide. It has got better tolerant to lower purity water, that also similar like alkaline fuel cell as well, and also large scale system available in the megawatt level as well. Compared to PEM, like lower efficiency and dynamic response is not that fast as PEM, and it has also got like quite similar application as I mentioned in the previous like overall fuel cell. So it use industry, power to gas, steel ammonia production, green hydrogen project and so on. Now the second one, alkaline water electrolysis. So if you like compare the like previous one, so I mean in terms of like modeling that we talked about in electrolyzer, it has also quite similar, that we talked about empirical, semi-empirical, physics based, which also I mean it can be utilized here. Same like quite similar algebraic equation for voltage current relationships, and then combining chemicals with like simplified dynamics and physics based dynamics, I mean including all the like reaction, mass transport, thermal, electrical dynamics. So it is exactly quite similar in the previous cases. So again I mean you can see like the same equation, but only previous cases it was minus, right, because I mean that was producing, but here we are supplying. So you see only that positive voltage is coming here, but all other equation that activation over potential, ohmic losses, concentration losses, that's exactly quite similar equation. So all the equation is given. I mean I'll just leave it with you. I mean if you want to model either by using MATLAB existing model, or if you want to develop by on your own by just writing those equation, because in MATLAB you just write the equation as it is and you have to give all the input parameter, that is all. And dynamic also, I mean again this equation also, I mean quite similar. For example, here you have got in the capacitor, and then from the capacitor you know that how to calculate the current, right. So, C dV by dt, that give the current. So, this is the from KCL, current law. From that, I mean you get this equation, and then by using all other dynamics that we mentioned for hydrogen, oxygen, we talked about many times, and also tutorial my student also talked about. So, this is also quite similar, the thermal dynamics as like the fuel cell. So, again I will just skip that one. So, again I mean in the dynamics, depending on what sort of variable I mean use, but here the equation that I have shown, it has got like 4 state variable. So, if you go for either a small scale or a model, then your model would be like 4th order, and if you go for like eigenvalue analysis or something like that, maybe you will get 4th order A matrix, and that is going to give like your eigenvalue and so on. But again this is 4th order model, but it can be extended by using like the pressure dynamics, electrolyte concentration changes over time, degradation modeling. So, if you add that, even it gonna be like a 7 by 7 modeling. But again as I say, like yesterday, depending on your requirement, you can go like how complex the model that actually you want to use it. And using this dynamic model, again I mean you can do transient analysis, control design, or if you want to analyze the interaction with the renewable energy sources like wind, solar, system level simulation including hydrogen storage, and even like for prediction like predictive maintenance like diagnostic, fault detection, also this sort of model actually can be utilized. And here again I have given like some typical values, and if you want to calculate that losses by those typical value, you will get that losses. Again this is the activation losses, this is the like ohmic losses, and see this is the cell voltage for a single electrolyte cell. And the next one like anion exchange membrane, AEM electrolysis. So, again the technique is quite same. We again use like the same electricity, same like reaction only, different could be your membrane, where we use like anode, no sorry, this is like the anode, and this is like your cathode. So, this is like your membrane, but all the operation, all the like chemical reaction are quite similar, only due to the difference in the membrane. I mean you will get different performance, but this is again like the most popular one like electrolyzer, sorry like fuel cell. So, the PM again I mean this is one of the like most popular one, and many people are doing research with this one. So, again I mean it same that it use like a solid polymer electrolyte that actually give you like better efficiency and also very fast response. And as I say like that better efficiency means like lower losses, better also power density as well. So, again you see that similar chemical reactions. So, if you compare this, I mean here you can see that the hydrogen purity almost like 100%, this one more than 9, I mean around 99, but this one is like more, if you need like very pure hydrogen, then I mean this would be your best choice. And you see the difference in the here use like potassium or sodium oxide as a in the electrolyte, but it was like a solid polymer membrane. The dynamic response, this is like moderate, this is fast. Pressure, this one use a higher pressure. Capital cost, that's the only things. Disadvantage compared to the alkaline, that's capital cost is higher. And this is also more matured than this one. Already commercially available, but it's less matured than alkaline one. This one also, I mean, it's given like some typical parameters in case if you are interested do some modeling and analyzing the performance either as a like a fuel cell or like grid connected with inverter, converter and so on. So, this one probably I will skip again. I mean, same equation, there is no point just repeating because only difference I mean comes between these two dynamics, that your time constant would be different because this one will be having like faster response, but other than that I think there are not any significant difference. And we already also discussed yesterday that I mean starting from that initial equivalent circuit, anode, cathode, finally I mean people use this sort of equivalent circuit with a like capacitor and resistance like a parallel branch, and then we have got the series resistance. But this is exactly quite similar, the one that we discussed and also this implemented in the MATLAB model as well. In case I mean if you want to estimate parameter for a full electrolyzer, you can do like that experiment and then curve fitting process. I mean you can actually calculate. One of my student, I mean he calculated this parameter using the equation, and also you can see that some collected some data, and then from that given the data point he also determined some parameters, and using those equation actually at the end he actually measured that CD and tau A, and that's how actually finally he managed to get the curve which actually fitted with the its characteristic curve. So, that's how I mean if you have got a fuel cell, if you don't know the parameter, you can also do some experiment and then actually you can calculate the parameter. So, he did calculate parameter, although there was error, but it's not that significance, but it is not that very difficult. I mean using even like simple curve fitting method you can actually do that. And again like the previous one, I mean as I say, like if you could have like different sort of modeling, but at the end if you compare, there would be slightly difference, as I mentioned, like voltage, current, quite like the same way that one. But if you go for, if you are interested more about the power, then I mean then it's not. But if you more interested that you want to see the impact in the voltage, then probably better to use like the initial circuit, but the simplified one, the power cases, I mean it's quite giving the quite similar response. So, this is the last one, solid oxide electrolyzer. So, that we also talked about solid oxide water fuel cell as well, and here also I mean exactly same working principle, you will get the difference in the membrane, but other than that everything is similar. And again I will leave this one to read by you as well. Even like the chemical reaction is also quite similar. So, this is like the overall comparison of this the three main technology that alkaline, PM and solid oxide. So, as I mentioned previous cases, solid oxide fuel cell or electrolyzer both they use actually higher temperature compare these two. So, the PM have got the lower temperature, this one has got very high efficiency, but still this one technology is not that matured. So, still I mean as I said, this is quite like the popular one, and this is use water and steam, because you see this higher, very higher water, but in terms of purity this one actually have got the highest performance, close to 100% as I mentioned. So, in terms of application, I mean this one also have got many application, like other electrolyzer quite similar, you can see in different applications, but depending on the situation, I mean you have to decide actually which one actually you gonna use it. So, again this is just giving the summary. Application also, I mean I already talked about those applications, but again it has been summarized here, like when you have got grid connected electrolyzer, these are the some application that I mean it can be used like in the buildings, or even like as energy storage in different industry, fuel cell station, gas to power, even like for remote microgrid, and many of you already working in the microgrid. So, in the remote microgrid also, I mean you can actually use both electrolyzer or even like the fuel cell as well. So, you could have electrolyzer, that hydrogen, it could be like using as a heating in the residential area, in the fuel cell station, or even like commercial building, even for your like transportation or fuel to gas application. So, using all of this, I mean you could have a microgrid which also could have wind, solar, and some cases diesel, you might have other load as well. So, this could be like one of the good application for remote microgrid as well. Renewable energy based electrolyzer, that also can be utilized. So, now I am gonna give like some few research direction, and then I am also gonna show like one or two simulation using electrolyzer as well. Now again, I mean the research direction, I mean could be in many ways. So, I mean if you want to improve itself the technology, then as I say, like the technology itself more like the materials level. So, for example, if you want to improve the catalyst, which is again one of the current research direction. So, it could have that they are gonna have more efficient and more cost effective electrocatalyst. So, I mean as we mentioned the PM, that actually use very precious materials, but current research that I mean that we would like to have more efficient, cost effective, but at the same time we do not utilize like the precious materials. So, non-precious materials to improve the performance, both like anode and cathode reaction in electrolyzer. So, that is one of the research direction to improve the catalyst. Even I mean you could have further research to improve electrolyzer and membrane as well. So, you can explore like new electrolyte materials and membrane design to enhance like low conductivity, reduce the resistance, and improve overall efficiency in I mean different types of electrolyzer. So, you see that there is a resistance, and we did mention that there are some losses. So, having that very high inductive ion that could reduce resistance and losses, and that can contribute to improve efficiency as well. Cell and stack optimization. So, I mean also people are working like to apply optimization to have like better design, advanced cell like the configuration, that might be also minimizing or reducing the ohmic losses and improve the overall performance. And then these three are more like if you are working like as a material scientist, but as a electrical engineer, now you can develop better method to integrate electrolyzer with other renewable like solar and wind power to have a like a hybrid system that might have higher efficiency and better reliability. Because if you have single solar based or even like solar wind combined, whatever the reliability you get, if you integrate electrolyzer like in a more efficient and optimal way, maybe you will be able to have even like better efficiency than single system in the hybrid system. So that's one of the research work people are currently working. Also, I mean, to reduce the cost, you can think of scaling up like electrolyzer manufacturing capacity, and that's how you can reduce the cost through like better automation, standardization, and also optimize the whole supply chain. So, I mean, in one of the slide yesterday I showed the supply chains. So, in supply chains you see that there are so many things involved, like in the input side we have got different renewable energy sources, and then the fuel cell, and then fuel cell connecting with the different application, different materials. So, and if you use like sensor and remote monitoring, so the whole things, the supply chain. So, in many cases what we do, like for example, let us say as an electrical engineer, we are just focusing on to improve the inverter. Some of the people they just trying to maybe improve the some tiny part of the electrolyzer. Some of them working like for the inverter, but if you want to have actually the base system, then you have to go for the like the system level optimization. So, you are considering the whole life cycle or whole that value chain, and then you are optimizing the system level optimization. That also people currently doing like to improve the overall efficiency, not only the efficiency of the device level, but the system level efficiency. And in all other application, people are also using like artificial intelligence, machine learning, to optimize the electrolyzer performance, predictive maintenance. As I mentioned that this is also one of the area people now currently doing, that you have system like for example rooftop PV or electrolyzer or fuel cell. So, you could have like from remote that you are continuously observing the performance, either comparing the data using the original generation, and that's how, I mean, if you see that something like unwanted performance, then you see that you might have some fault, or even like that there might, I mean, system performance might be degradation after 5-10 years, and that will give you some notification that you need either maintenance or you need the replacement of some parts of the overall system. So, that also I mean can be done using machine learning and also artificial intelligence. We talked about like the longer life. So, that also improved or longer life duration, also the reliability. So, people also working in that perspective to improve the durability and reliability of electrolyzer, mainly that when you place electrolyzer in very harsh operating condition to ensure like that long term performance and reduce maintenance requirement. So, people are also working in those areas as well, and as usual as I mentioned that cost reduction, that gonna be continuous research, like to identify maybe better materials, better way to optimize the whole things, the reaction, improving the reaction. So, all possible way, I mean people are trying to reduce the overall hydrogen production cost, because the cost involves not only the fuel cell cost, but the cost that is coming from the whole value chain. So, that is also like one important research direction people are working. As a system level integration using like a multiple electrolyzer. So, I saw some work people are doing that, for example, alkaline have got comparatively like dynamics is moderate fast, but the PM we say that it has got very like fast dynamic response. So, if you have got a system, right, in the power system some of the dynamics, I mean when you have got like instability problem, you will see that some of the dynamics is very fast and some of the dynamics is comparatively slow. And even like the stability, some of the stability problems happen due to the fast dynamics and some of them happens like slow dynamics, right. So, in your system, I mean if you have got a problem, so by using like different types of or different combination of multiple electrolyzer, also you can address different types of stability problem in the system as well. So, that is also possible by using multiple electrolyzer. People also working like direct coupling of wind, solar with electrolyzer using like specialized, but that is more like how you can have better power electronics coupling that can give you like very constant power supply instead of fluctuating output as you normally get from these devices. So, that is more like the improve using the better power electronics to get like constant output power, and that is actually sometimes quite essential for certain applications. In some application, if you have got slightly bit fluctuating power, it does not cause that much problem, but in many cases like in sometime in the lab, in sometime in like electrical drives application, sometime you need like a very constant power output that actually can be done using power electronics and combination of these three technology. The grid stabilization, as I already mentioned, that we can use like a control load to minimize like the network congestion and other stability problem. Also, I mean people are working like that, we having like different types of model, but which model is good for what study, and then not only simulation, but also conducting some experiment to validate your model for different stability, voltage, frequency regulation and so on. The control technique, probably today I mean we will have one lecture on control technique. Also people are working like which control strategy might be best for electrolyzer to optimize their operation like in response to different grid condition and maximize the benefit of integration. So, one controller might not be I mean good for all application, depending on the grid condition and operating condition, you might need to find out which control technology give you like the best performance. And then hardware technology, as I say, like sometime if you use MATLAB and if you have got like in a very large model, and mainly if you use like discrete or continuous type modeling, it takes sometime very long time to do the simulation. That's why sometime we move to like other commercial software like PSCAD, Power Factory. So, instead of using like only MATLAB, if you use MATLAB plus hardware in loop like in OpenLATE, which has got very fast computing power, then you can do like whatever what if study, like if you want to do like any scenarios that normally happens in the real system, it can be done in the hardware in loop testing. So, sometimes we also do a hardware like only like simulation, no hardware, but also it can be done simulation and hardware as well. But at the end, I mean we also need to not need to entirely rely on the simulation. We also need to do some experiment and pilot project to validate our model, to validate our design, to validate our controller performance. So now I'm going to show you few simulation result. So I mentioned like that it has got very fast response, right. So here you can see like how many second or millisecond it taking to respond the electrolyzer, either ramp up or ramp down, either like when it is a load, like the input power either taking more power to produce more hydrogen or taking less power to produce less hydrogen, right. So that's like either ramping up or ramping down. So you see here at this point we are asking electrolyzer to ramp up the power. How many second or millisecond it taking? Like sub-second, right. So you see that it is like very fast, right. In both cases, like stepping up, ramping up or ramping down. So depending on how much you are asking to ramp down, is immediately start and taking like less than like second, whatever power you asking to do it. You see that is very fast, whatever command actually you are getting. So that's actually giving flexibility and also to solve the stability problem like to the grid, from the demand side. Again, electrolyzer is like a connected in the demand side, not in the generation. So we are just using the demand response type things, to control the to stabilize the grid. So normally demand response we just use for reducing the peak demand, right. So when during the evening time we have got very high demand, I am not sure it had happened, but in Australia actually it's really happening. So during the peak time, the electrical grid operator, they provide some incentive that if you turn off your washing machine, you're going to get $5. So I'm just giving one appliances. So you might have different appliances that you might not need to use that peak time, and the grid operator, they are giving incentive so that the demand on the grid actually reduce. That's how the grid will not face any problem, either power quality or stability. So this is again just reducing the peak demand, but here if you have the electrolyzer, it actually can be utilized to solve the stability problem, and also it's giving more flexibility what actually you can do in your system. So there are some simulation we're going to do, but it actually use the USS system because their data was like available. So here you can see that the system include both generation, then that after generation we have got step up transformer, then we have got transmission line, different level of voltage, then you have got the substation. It reduce step down voltage, but it's like the sub transmission level, and then after sub transmission we can have a distribution, but again like the primary distribution. In many cases it could be 11 kV, many cases 13 kV, 4 kV, depending on country and also the location. And then you have got the secondary level. In USA could be 120, but in Australia actually 240. So you have a system like this, and then in the demand side, like you have like your electrolyzer network, and depending connecting with that. So here you can see here in the first graph, that electrolyzer power consumption. In the second one, you can see that the power coming from like solar. So this solar power, when it's coming like this variable solar power, what is happening in the sub transmission level as a load, like with this only PV, when we don't have electrolyzer, you can see that in the in the substation, that's I mentioned here, in the substation levels you see that voltage, but when actually we are connecting this electrolyzer, what is actually doing that electrolyzer? So that's fluctuation that you can see from solar, that fluctuation actually will be minimized by using the electrolyzer, because that also taking the power, like very input power which is quite fluctuating, right. So that fluctuation coming in the solar, that's how gonna be reduced by electrolyzer, and that actually can reduce the fluctuation in the voltages as well. So here you see this is the maximum fluctuation accepted by the grid operator, which without electrolyzer sometimes it's exceed that requirement, but when you connect electrolyzer, it actually going within that limit. Same like that one like voltage, even this one like frequency. So when in the same system we didn't have any electrolyzer, and here there was sudden disturbance, and then the frequency was going up, because probably there was a disturbance, that demand actually going down. So you can see there is a jump in the frequency, but when you have got electrolyzer, again this is giving the frequency fluctuation almost like a constant. So even like in this is like in two different cases. In both cases you can see that when you have got electrolyzer, the frequency is also much better, and again that's actually possible because this sub-second response time, that's actually contributing to reduce that problem as well. So this is another example that here we have got fast charging electric vehicle station, which is connecting in the distribution system. Then you have got like different buildings, PV, wind, and then you have got the hydrogen storage and electrolyzer with inverter converter. So again, when we didn't have that electrolyzer, only for fast charging EV, you can see that that battery and solar PV, and then we have got that constant building demand. At the end, through this, the net load would be like this. Combining all of this, so your net load would be like this without electrolyzer. So you see that the grid will see that this is the power requirement from the grid. So it's quite fluctuating, but once we connected the electrolyzer with that system, when we combining all that individual power response, you see the grid will see that this is the demand from the grid. So all that fluctuation that is happening through PV and fast charging of the electric vehicle, everything has been addressed with the electrolyzer. So yeah, so you see that electrolyzer, quite essential technology, not only to produce hydrogen, but also it can provide flexibility, and also it has got very good control capability to solve the voltage and frequency problem. Thank you. Hope now I think you have got some idea about the electrolyzer, and some of the research was going on, and if you are really interested, probably you have some idea what you can do in your research group. Thank you. Thanks for your attention.
Electrolyzer, the output is chemical energy, hydrogen.
No, for electrolyzer, input is the electrical energy.
Electrical energy.
Electricity.
Electricity.
Yes.
Before this, there is, I think after this, there is one more slide.
Hydrogen gas.
Okay.
So this hydrogen here, it is using for heating. This hydrogen is using in the fuel cell to produce electricity. This is again building for heating, cooling, and this is hydrogen in the fuel cell, pump station.
Okay.
And you see in the input, the electricity.
Electricity.
But definitely there is another input, water as well.
Okay. Okay. Sir.
As your study, that some
Because here actually we didn't compare with the battery, we just compare with the fast charging
okay.
EV. But again, with the battery, that there are pros and cons with the battery and hydrogen. So battery, if you just need short term storage, then battery might be okay, but if you need like the longer term hydrogen, but in terms of providing stability, actually I haven't compared, but you can do compare. Battery also has got a fast response as well, but which one might be providing better for voltage and frequency, I haven't done it, honestly speaking. But this is one area, probably you can do further research. But I believe, because this is also like have very fast response, even it's not better, it would be comparable, like the ancillary service that you are getting from the battery. But what is happening, like the battery is already matured and already using the grid, already established. But hydrogen, if you want to make a fair comparison, right, you have to install it and you have to measure the real performance from simulation. You can't say that probably this is better. So you have to have demonstration project, you have to have real implementation in the grid, and then you need to also allow this one to participate in the ancillary service, right?
Okay.
Unless you able to do it, because what happened, in the system still there are many inverter, but not all the inverter participate in the providing control service, right? Some of them is just like giving like the power input to the grid. It doesn't have any capability to providing any ancillary service. So even if you might say that some small scale electrolyzer is connected with the grid, but still, they are just like a load. They are probably still not participating in the ancillary market to provide any service to the grid.
Okay.
But again, that's a good question, and probably again we need further research and development to find out which one is best. I think instead of best, the better would be that we have hybrid energy storage system that gonna give you the best performance. So you could have even like battery, fuel cell, or even you could have super capacitor, battery, fuel cell. Then you have like the better combination, and for example that the super capacitor even have got very high, very fast response compared to the battery as well, right? And if you need very higher power output within very short period of time, that super capacitor can do, but battery cannot do that. So again, the hybrid option would be the best solution.
Okay, sir. Thank you.
While we are integrate this electrolyzer with the grid, so one of the slide you shown that the power curve is flattened, right? Power curve is flattened. One of your slide.
Yes, yes.
Electrolyzer current or what for?
So this one is not power. This is grid. From the grid, when all the system is connected, the grid shows that the demand is something like this. Although this is not the actual demand, but if you add all of them,
okay.
so the final response is like this.
Yeah, but this, my question is that, sir, how we can get, means we can control the stack of the fuel cell, or we are controlling the current of the electrolyzer?
So we are mainly controlling that the input electrolyzer current.
Current means we are controlling the current.
Yes.
Okay.
Fluctuation control graph you had shown, see, that electrolyzer can be used as a fluctuation controller. How?
Yeah, I mean, the electrolyzer input you can control. Like, I mean, I didn't show the control purpose, but that definitely is a control. So what we are saying that when we having that fluctuating demand by combining like PV and fast charging, right? So that fluctuation actually being taken or minimized by that input power or input current that's coming to the solar. So things like in your home, right? So sometime in your home, if you have, let's say, non-linear load, right? And this non-linear load, sometimes what happens, it produces harmonics, right? But sometimes if you like there is already converter available with your either battery or even like electric vehicle if you connect with the grid. So although this load has got harmonics, but that harmonic component is supplied by your converter. So grid, it will not show that you have harmonics in your home, although you have harmonics, but that is compensated by the local inverter. So this is also quite similar. You have fluctuating demand from the grid, but that fluctuation is taken by the fuel cell. At the end, grid will see that it has got constant demand from the grid. Although individually it has got fluctuating, but when you are combining all of this, you are getting like a constant.
Thank you, sir.
So for like positive fluctuation, negative. So each of them cancelling each other. PCC.
Okay, thank you.